Anybody that has ever filled up their car at the gas station has seen the familiar 85, 87, 91 numbers on the pump. Those are the octanes of the different gasoline grades. These different grades are necessary because modern day engines have the requirement for higher and higher octane fuel. Higher octane numbers reduce the tendency of a motor engine to knock. The process unit operation in a refinery that increases octane number is called a reformer. It's such an essential operation that there's a reformer in virtually every refinery in the world. At a high level, there are three fundamental types of hydrocarbons: paraffins, which are straight-chained and branch-chain molecules; naphthenes, or cyclical hydrocarbons; and aromatics, which are planar molecules. Each of these different hydrocarbon molecules has different combustion characteristics, with aromatics having the most favorable characteristics. Thus, the goal of a reformer is to convert as many of the paraffins and naphthenes into aromatics. The reaction is endothermic, meaning that the temperature of the reaction material cools as the reaction proceeds. Thus, heaters are required to reheat the feed material back to reactant temperatures in subsequent reactors. It usually takes 3 or 4 reactors to reach the desired octane target, with the actual number of reactors depending on feed quality and how high the octane number that the plant wants to produce. A huge side benefit of a reformer is that the reforming reactions produce a large quantity of hydrogen, which is subsequently used in hydroprocessing units throughout the refinery. Feed can come from several sources. The usual and largest source is naphtha from the crude unit, though there may be other sources such as naphtha produced in the coker. Feed is combined with recycled hydrogen at a relatively low pressure before being heated in a furnace up to reaction temperatures, which are typically about 1,000 degrees Fahrenheit. The reaction occurs across a very expensive platinum catalyst. There are 2 types of reformers in operation today: semi-regenerative and continuous. These different designs refer to how the catalyst ultimately gets regenerated. In a semi-regenerative reformer, like the one shown here, there is a series of separate distinct reactors with fixed catalyst beds. Over the course of months, the reforming reaction produces coke, which causes the catalyst to deactivate. To compensate, operators raise reaction temperatures in order to obtain the desired conversion rates. However, eventually the reactor will need to be shut down and the catalyst regenerated. A typical cycle is 1 year before regeneration is necessary. The other type of reformer is a continuous reformer. In this design, the reactors are physically stacked on top of one another. The catalyst then slowly moves through the reactors over a period of a few days to a week, becoming more coked up as it moves through the system. In this design, there is no need to raise reactor temperatures since catalyst activity at any point throughout the system remains relatively constant over time. Upon leaving the last reactor, the catalyst is blown via a series of lock hoppers into a regenerator, where air is contacted with catalyst at high temperatures to burn the coke off the catalyst. Clean catalyst is then returned to the top of the first reactor. The size of the individual reactors in both designs is always opposite to the size of the associated reactor furnaces. The first reactor only contains 10 to 15% of the total catalyst volume, since any cyclical hydrocarbons in the feed material are quickly and quantitatively converted into aromatics after contacting the platinum catalyst. The reaction produces a large temperature drop across the reactor bed, necessitating a rather large furnace to reheat the material back up to reaction temperatures. In the last couple reactors, the goal is to convert paraffins, straight-chain and branched hydrocarbons, into cyclical hydrocarbons, which are then quickly converted into aromatics. However, this becomes increasingly more difficult as the feed proceeds through the reaction circuit. Since there is less reaction occurring in each subsequent reactor, there is also less temperature drop. After exiting the reactors, the hydrogen and other light gases are separated from the liquid in the separator. Excess hydrogen leaves the unit under pressure control and is available for other refinery units, such as hydroprocessing units. The remainder of the gas is compressed in a large centrifugal compressor and recycled back to the first reactor. The liquid from the separator is sent to the debutanizer, where LPG material, propane and butane, is separated from bottoms reformate. This reformate stream is one of the principal streams used to blend various grades of gasoline.